Hello, I'm Ryan from High Desert Math Tutor, and today I want to talk to you about a slightly more challenging optimization problem from calculus. So the question is, a fence is to be built to enclose a rectangular area of 310 square feet. The fence along three sides is to be made of material that costs $6 per foot, and the material for the fourth side costs $13 per foot. Find the dimensions of the enclosure that is most economical to construct. So before we really jump into this question, I want to point something out about cost. So in general, so let's say good to know, total cost is equal to the rate you have to pay. So how much you pay, say, per foot or per dollar or per cup. So the rate you pay per foot times the amount you want to buy. So good to know. The cost, just in general of anything, is the rate you pay for a certain amount times the amount you actually want. Now, looking at this question, we see that we're dealing with a rectangular shape. So the enclosure is rectangular. Now, if we were to draw a rectangle, we see, not that great. So if we draw a rectangle, we can now reread the question and kind of put some of the information that they've given us in this question on the rectangle to help us kind of see the situation more clearly. So the total area here is going to be 310 square feet. Now, two of the sides are going to have one dimension. So let's say this is length and this is length. The other two sides will have the same dimension, width and width. Now we know three of the sides here are going to cost $6 per foot for the material to make this. So using rate times amount, let's say that this bottom side is the fourth side, which is slightly more expensive. Now the other three sides are going to cost $6 per foot. So the cost of this side is going to be $6 times that length. This side is going to be $6 times that length. And this side is going to be $6 times the entire width. Whereas the last side on the bottom, this one is going to be $13 times that width. Now, our overall objective is to find the dimensions, so say the length and the width of the enclosure, but we want to find the dimensions of the most economical enclosure, so the one that's most affordable or cheapest to construct. So what that means is we really want to look at cost overall, and with cost, we want it to be minimal. So we want to minimize the cost. So a formula we can come up with for cost would be the cost overall is the cost of each side put together. So if we start here and work our way around, we see we have 6 times L for the cost of this side. Now the cost of this side is going to be 6 times L plus the cost at the top is going to be 6 times W plus the cost of the bottom is going to be 13 times W. And I only put these check marks so I could account for the sides that we have already put in the formula. So the total cost is going to be 12 times L plus 19 times W. So if we know the length and the width in terms of feet, we can have the total cost using this formula. But where does this square footage come into play? Well, since we're working with this problem um, in typically a first calculus class, we need this formula to have only one variable that we're working with, either length or width. And right now we have two variables. So we need additional information to substitute one of these variables for in terms of the other variable, to replace it so we have something that's equivalent to this in terms of, say, length. So we can use the area to get this information. So we know that area is equal to length times width. And if we want to eliminate the width from this formula, we need to solve for width here. So we can divide both sides by length. We find the width is area divided by length. And now we can substitute that into this formula to get rid of the width. So one last step before we substitute, I want to make note that the area is actually equal to 310 square feet. And now this is going to be useful, first of all, here, so that we can get a formula for cost that is all in terms of length. But this will also be useful later on, as you will see. So a good checkpoint now. We have a formula for cost. This formula is all in terms of the same variable, length. And before we move on, we want to ask ourselves, does this seem like an appropriate candidate for the objective of this problem? So remember, kind of in solving this problem, what we need is a formula that describes the cost of this enclosure, and we need this formula to be something that has a minimum because we want to minimize the cost. Well, this is a linear term. This term is rational where the only variable is in the denominator, and whenever you have this combination of terms, you always have a minimum in this scenario, at least for the positive values of L. So we will have a minimum here, and if you wanted to check this for yourself, you could throw this equation into Desmos or any other graphing calculator. But since we're solving this question algebraically, so only using algebra and calculus on the board here, we actually need to work on finding the minimum by other means, which what we do in a calculus class is we take the derivative and then we find the critical values. So if we take the derivative of this, c prime, we're going to get 12 minus, now let's do that 19 times 310. So what we get is negative 5,890 divided by L squared. And so this is the derivative. Now to find the critical value, we need to set this derivative equal to 0. And the approach I like to take in this situation, 12 is positive, this whole thing is negative. Now since 12 is already positive, I want to make this positive while also working on solving for L by just adding 5,890 over L squared to both sides of the equation. And the reason I like to do this is because many people make mistakes when negatives arise in an equation. And this was a way for us to just get rid of a negative by adding instead of multiplying or dividing. Now we're solving for L right now, so we can multiply both sides by L squared. We get 5,890 equals 12 times L squared. If we divide both sides by 12, we're going to get L squared equals 5,890 over 12. And final step of the algebra is to get rid of the square by taking the square root of each side. But a key thing, and now I'm gonna go ahead and put L on the left side. So a key thing that you have to remember here is anytime you cancel a square using a square root, you're going to get plus or minus in your answer. And here we need to ask ourselves, which is the appropriate answer for this scenario? Well, L represents a length, and length is always positive. So that means we are going to stick strictly with the positive answer here. So it may be hard to see, but this, because it's a root, but this is the length of the enclosure that minimizes the cost while still maintaining the appropriate area. Now, to find the width, we can make use of this formula right here a second time. So we see that width is equal to 310 divided by the length. Well, here, that's going to be 310 divided by the square root of 5,890 divided by 12. Now, both of these are a little bit intense looking, but if we throw them in the calculator, we can find an approximate answer that is typically what we'd want in the real world when working with this sort of problem. So to be clear, if you're doing homework online or working on tests, often this is the perfect ending point for this sort of question, where you can throw this whole thing in as an answer online, or most math teachers would be totally happy with this as a final answer on a test in terms of length and width, as long as you state your answer appropriately. So let me go ahead and actually state the answer appropriately, and then for fun, we can go ahead and find the approximation of each of these so we have a better understanding what the actual length and width will be. So as a final answer, what we want to say is the dimensions. What that looks like in general would be length times width. And what this is this would be the length by width. So like 10 feet by 20 feet, something of that nature. So what we could say is length here is the square root of 5,890 over 12 by the width would be 310 divided by the square root of 5,890 over 12. So this would be a totally valid, exact answer to this question. But like I said, for fun, we'll go ahead and find the approximation of the length and the approximation of the width so we have a better idea of what we're working with here. So I'm going to go ahead and round each of these to the nearest foot. So what we get here is 22.15475, blah, blah, blah. This is approximately 22 feet. And here, what we have is 310 divided by the square root of 5,890 divided by 12. So this is going to be approximately 14 feet. So if you were taking approximate answers where you round to the nearest foot, you would have 22 feet by 14 feet as a final answer. But as I mentioned, in math classes, we typically like the exact answer, which would include the root and this root here. And typically in a math class, like a calculus class, we're not that concerned about having a square root in the denominator. So once again, these would be totally valid answers for most teachers, most classes, but this is how you want to state your final answer if you're doing this sort of question on paper or on a test. Again, on paper overall. So yeah, this is just an example of a slightly more challenging than typical optimization problem, and we're taking the calculus approach to solving this, where we actually take the derivative, find the critical values, and that's how we find the optimal length to minimize the cost, and then after that the optimal width to minimize the cost also. You could also solve this question algebraically by just, or not algebraically, but the typical algebra way, by simply setting up this formula and plugging it into a graphing calculator. So either way is totally good, but that's how we do it. So I hope this is helpful.